Hello, we are Team Electra. Today we are going to talk about fundamental geometric algorithms. These are our team members' contribution. I am Prince Cyril Deva. I'll be the first one presenting today, starting with knot insertion and knot insertion algorithm. The next team member Ravi Kiran will talk about surface knots and geometric modeling lab, followed by Sai Pawan with knot refinement, Bezier decomposition, and design examples. Finally, Lindsay Fields will talk about knot removal and degree elevation slash reduction. Knot insertion. Let's C to the power of WU be a NURBS curve defined on U0 to be a non-decreasing sequence of real numbers where U sub I are called knots and U is called a knot vector. This gives us the equation C raised to the power W U summation I is equal to 0 to n sub I comma p of U pi W, where P defines the control points of the curve. Now if we insert U bar into U, we get a new knot vector U dash, where U dash is also a non-decreasing sequence of real numbers. If U sub U and U sub U dash denote the vector spaces of the curves defined on U and U bar respectively, then clearly C to the raised to the power of WU has a representation on U bar of the form C raised to the power WU summation I 0 to n plus 1 n bar IP of U Q sub I raised to the power of W, where n bar IP of U are the pth degree basis function on U bar. These are some of the applications of the knot insertion: adding control points to achieve increased flexibility in shape control, subdividing curves and surfaces, evaluating points and derivatives on curves and surfaces. Generally, the process of determining Q sub I raised to the power of W in the above equation is called knot insertion. By setting and solving the system of linear equations, we get this equation that we can see here. By using previously defined properties, property 2.2 to be exact, and implying, we get summation I is equal to k minus p to k n sub I comma p of U p sub I to the power of W is equal to summation I is equal to k minus 1 to k plus 1 n bar sub I p U q sub I raised to the power of W for all U sub k U sub k plus 1 for these ranges of I. Now finally combining the above two equations with linear independence of basis functions, we arrive at p sub I W is equal to q sub I raised to the power of W, and p sub I raised to the power of W is equal to q sub I plus 1 raised to the power of W for the ranges of I. If we if we express n bar for a range of I, we can arrive at the equations shown here. Now we write n bar sub I for n bar sub ip of u. We get these equations. Due to the time constraints, we have to skip some of the steps. Anyway, finally we arrive at this equation that you can see here. And next slide. Now, by equating coefficients and using the naught vector u in place of u bar, we obtain, by equating it to 0, we arrive at the equation that you can see here. And now for all ranges of I, we set alpha sub I is equal to u bar minus u sub I whole divided by u sub ip minus u sub I, 1 minus alpha sub I u sub I plus p minus u bar by u sub I plus p minus u sub I. Now, by using the linear independence of the basis function, we can conclude that q sub I raised to the power of w must be equal to alpha sub I p sub I w plus 1 minus alpha sub I p sub I minus 1 w for k minus 1 plus p is less than equal to I is less than equal to k, which allows us to get the final equations by computing all the new control points q sub I w, that is q sub I w is equal to alpha sub I p sub I w plus 1 minus alpha I p sub I minus 1 raised to the power of w. Here we can see the example for knot insertion. If we set p is equal to 3 and knot vector u and the control points p0 to p7, then when we insert u bar is equal to 5 by 2, then we can compute the new control points. On the right hand side, you can actually see how the calculation takes place. As we can see, the results are in fractions from the previous control points. The graph that you can see on the right represents the new basis function before and after the knot insertion. And if you see to the right side, to the left side, sorry, control polygon, you can see the control polygon after inserting the u bar. Inserting a knot multiple times. Sometimes we need to insert a knot multiple times. Suppose u bar belongs to u sub k plus 1 has a multiplicity s, and it is inserted r times, where r plus s is less than equal to p. Then we denote the ith new control point in the rth insertion step by q sub I comma r raised to the power of w. This equation that you can see here represents inserting a knot r times into the NURBS curve, which you can see right here. Here we see an example of inserting a knot multiple times. Here, if we set the multiplicity s is equal to 0 and r is equal to p times, Then we can generate a triangular set of control points. The outer control points and the inner control points are discarded. The final control points are obtained by transversing the resulting table in a clockwise fashion, starting at the top of the first column generated. Let r is equal to 3, the curve is defined on 0, 0, 0, 2, 3, 3, 3, 3. Now we end up with the following cubic. This is obtained by inserting naught 3 times into the original curve. We can see the previous control points and the new control, and here are the new control points after they have been inserted. Here is the algorithm for knot insertion. This is much simpler than the math discussed in the previous slides. This algorithm computes new curve corresponding to u bar r times, where up and uq are knot vectors before and after the knot insertion. Well, this slide shows the applications of knot insertion. The application shown here is splitting a cubic curve. If we start with the original curve C that you can see here, and then we split it at u is equal to 1 by 2, resulting in the points C1 and C2, which are then split at 1 by 8 and 3 by 8, resulting in the following points C11, C12, C21 and C22. And from the next slide, my team member Avikiran is going to take over.